Ann came in and asked me, I go over some problem earlier, and the answer is, of course, you don't even have to get here early to do that. If you ever have a homework problem you want to, it's confusing or you want to see, beginning of class is a good time, and if you don't feel like it'll be beneficial for the whole class, you can, of course, come to office hours. Some of you probably noticed I write out notes before I come to class. In high school, I could wing it, met the class every day for an hour, and if I messed up or went in the wrong direction, I could fix it the next day. I'm trying to be a little more organized. We don't have spelled Schoenbrun wrong. Well, this is the first time I put these little headings like Rolle's theorem or example. This is the first time I put on here opinion. Opinion. Opinion means I gotta say something, but I don't really know how to go about this. Okay, I'm just gonna read it. I'll try that. Today we are going to learn about Rolle's theorem and the mean value theorem. There is an irony involved with these theorems. They are both critical to the subject of mathematical analysis, of which calculus is mostly considered a subtopic. Analysis, the area of math that examines the underpinnings of calculus. The irony is that even though every calculus class students are taught about these, they will not be very useful to you. I'm going to show you a couple examples on how they can be used in calculus. But what I'm trying to get at is they really are important in upper level math, and yet they're not that important here yet. They find their way into the curriculum. So I'll do what I can to make it entertaining so you'll absorb it. But again, if you feel like, why, then you're on the right track. Why are we doing this? Okay, so Rolle's theorem is, I'm going to do it pictorially first, and then we'll get the details. You have some function. You can make it look like a parabola. And it has 2 points, A and B. And as part of our assumption, f of A equals f of B. We have to know that. We also need to know that this interval here, AB, is continuous. Doesn't work necessarily if that's not the case. And on the open interval, AB, it is differentiable. You can find a derivative all the way along here. And what Rolle's theorem says is that there's some C in between A and B where f of C equals 0. That is, there's a horizontal tangent to some point up here. Now, what I stated is true. The picture could vary a little, as long as you follow the same rules. For example, you could have A over here and B over here. And, well, actually, we have two C's here. We have a C here, call it C1 and C2, where f of the derivative, the derivative is 0. That's Rolle's theorem. Okay. Well, why is that so? Nothing on my sleeves. I'm just going to hand wave a little here. Like the function, we can show that the derivative is continuous. That means, for every value, between any two values, it's going to have all the other values. So in this diagram, you can see, since we have a positive derivative here, a negative derivative here, between the positive and the negative, we have all the values. One of them is going to be 0. The theorem that tells us that is the mid-value theorem. It just says if you have some point A and some point B, and have some function, f of A and f of B, essentially it says that all the values between f of A and f of B will appear somewhere on this function. There was a problem with some monks that, a while back that kind of uses that idea. A monk goes up the hill at, in the morning, and he comes down in the evening, and, show that he's, at some point he's there at the same time. You can use this theorem. All right, so that's Rolle's theorem. What can I do with Rolle's theorem? Well, there's some clever things, even in calculus. One thing you can do is you can say, well, physics, say you throw a ball up in the air, just baseball. You can say that, due to Rolle's theorem, that at some point its velocity is going to be 0. It's going to go up and down, and at some instant its velocity has to be 0. Well, how do we know that? Well, it starts off, in your hand, and it ends up back in your hand. Its velocity changes. First it's going up, then it's going down, and its velocity is continuous. So at some point, according to Rolle's theorem, it's at the top of the arc, it's going to be 0. Okay, that's not that clever. This one's a little more clever. We have a function, f of x equals x cubed plus x minus 1. An aside, how many roots does this equation have? Roots being, where it's equal to 0, where a function, crosses the x-axis. How many roots? Has 1. Well, x funny because what we're going to try and prove here is that it has exactly one, gosh, that is stupid today. Exactly one real root. And you're sort of right, but that's not the answer I was looking for. How many roots does the polynomial function of degree 3, how many roots does that have? Okay. All right, we'll backtrack a little. And mental theorem of algebra. Does anyone remember the fundamental theorem of algebra? Fundamental meaning, could mean like the first foundational or the most important. All right, that's fine. A little trip through memory lane. So for a long time, I thought that the fundamental theorem of algebra was that if you have a polynomial of degree n, it has n roots. Now the statement is true, that's technically not the fundamental theorem of algebra. Fundamental theorem of algebra says if you have a polynomial of degree n, it has a root. Okay. But if it has a root, and there's another theorem that says, well, you can kind of divide out by x minus that root, and you'll get a polynomial of n minus 1. You can show that there has to be n roots. We spent a lot of time here on this, that's okay. I'm just gonna go for broke here. I don't really know what the fundamental theorem of arithmetic is. And that goes back to like 4th or 5th, well, probably 7th grade before they would tell you this. Anybody? Fundamental theorem of arithmetic. What are they teaching in school today? You Zoom. Okay, you all know this. You just don't know the name. If I have some number, like, say, 63, I can break 63 up into its prime factors. Anyone know the prime factors of 63? Yes? 3, 3, and 7. Exactly correct. The fundamental theorem of arithmetic says, aside from, switching the order, there's only one way to do this. So there's no number where you can break it up into one set of primes or a different set of primes. All right. Fundamental theorem of algebra, you might as well think of it as it's of degree n, so it's going to have n roots. But our problem is to show that it's exactly one real root. Just one, no more. There's 3 roots, but they're not real, what are they? They could be imaginary, or they could be a little more complicated, right? It could be complex. Okay, well, let's first of all show that there is a real root. So let's pick a big number. And that's going to be 1009. Okay. Now let's pick a little number. It's going to be okay. So between -10, 10, we go from down here to up here somehow, probably not a straight line, and this intermediate value theorem tells you that every value exists, and since 0 is one of those, we have a root. We don't know what it is. We don't have to know what it is. We just know there is a root. Okay? Now I told you this had something to do with Rolle's theorem, right? So we better get Rolle's theorem here. Suppose this has two roots. We're going to just call them A and B. More than one root. Sounds like a condition of Rolle's theorem. It's a polynomial, so we know it's continuous everywhere. And it's differentiable everywhere. So far, we can apply Rolle's theorem. Rolle's theorem says between A and B, there's a C such that f prime of C is going to be equal to 0. Let's test that out. What's the derivative here? F prime is 3x squared plus 1 equals 0. How are we going to find a C, a real C, that makes this 0? That's the clever part. Everyone see that? You can't. There's no number you can plug in for x where you get a 0 here. So our assumption that there are two real roots has to be wrong. And that's how you prove there's exactly one real root. Okay. I always thought that was clever. Again, not crucial stuff, but part of our curriculum. Questions before I erase this? I'm going to leave the diagram of Rolle's theorem up because you'll see how the mean value theorem is just a little bit more complicated. So again, I have a function, and it has values at a and b. It has an f of a and f of b. This time, f of a and f of b are not equal. Now, if I connect these points with a line, it's going to have a slope. And the slope's going to be f of b minus f of a over b minus a. The mean value theorem has these, except for this, has the same requirements. It has to be continuous on the interval and differentiable. And the mean value theorem says that there must exist a C such that the tangent to C has the slope of this line. That's the mean value theorem. Amazing to think it's so important. It just seems very limited. It doesn't tell you what C is. It just tells you there must be one. Well, looking at this diagram, it seems plausible. We could just draw it a little more clearly here. I mean, another way to look at it is there's a line parallel to this line. It's tangent to the function. Okay, that's the mean value theorem. So what can we do with that? Well, an example. Let f of x be x cubed minus x. And this is on the interval 0 to 2. Again, since it's polynomial, we know it's continuous, and we know it's differentiable. We know that f of 0 equals 0. F of 2 is, what, 8 minus 2 is 6. So the mean value theorem tells us that, well, if we look at the slope between these 2 points, it's going to be 6 minus 0 over 2 minus 0 equals 3. So it says that there's some C such that the derivative of C is 3. Well, let's find that. Okay. Derivative of x is 3x squared minus 1. We said 3x squared minus 1 equal to 3. We get 3x squared equals 4. X squared equals 4/3. And now we find the square root. And we say, well, plus or minus 2 over the square root of 3. But wait a minute. We're not interested in the negative result, are we? I mean, negative 2 square root of 3 is not between, it's not on this interval. It's out here. So really, 2 over the square root of 3. So that's our C. We're gonna discussion going on. I don't want to interrupt it. Keep going. Okay, so we are going to do something real with this theorem. It's not going to be of much importance to our class, but it'll give you a feel for the type of things that mathematicians like to do. Let's say you have some function. And let's say on some interval here, call this A and D. That on that interval, the derivative is 0. I'm kind of lying here in this diagram. Maybe I should indicate where I'm lying. Blue. So what we want to do is we want to prove, given that we have a continuous function, on somewhere there's an interval where the derivative is 0, we want to prove that f of x is constant. Okay. So, actually, I take that back. You gotta get this. You gotta be very, very careful here. It's constant on AB. Okay, I didn't state it right. Yes, it's right. I have a function. It's defined on this interval between A and B. And on that interval, the derivative is 0. Okay, that's what I show. So I don't really know what this looks like. All I know is the derivative is 0 on that function, on that interval. And I want to show that it therefore must be a constant function. Okay. And I'm going to use the mean value here. So when you do it is you say, all right, let's choose two numbers in between A and B. two numbers. So by the mean value theorem, there's a c equal to, there's a derivative at c equal to f of x1 minus f of x2 over x1 minus x2. There's a c such that this is the case. But we know from our assumption that that's 0, right? That's the assumption that the derivative is 0 on that interval. So if that's the case, we can multiply through by x1 minus x2. And we can see that f of x1 equals f of x2. So we've shown for every x, every pair of x's, the function is the same. And that's what we wanted to prove, that it's a constant. So this is the kind of, it seems very simple, but in analysis we prove things that are seemingly very simple, often very hard to prove. And we do this because we want a very solid underpinning to our calculus, which you're getting for free. All right, we're just going to take a break now. If any questions, I'm here for a few minutes, and then we'll move on. Does anyone here have one of those fancy, like, TI calculators? Okay. I think anyone else who has an iPhone or an Android can probably get an emulator, meaning it works the same way, except during an exam where you're not allowed to use your mobile phone. It's really useful to have one of these calculators when you're kind of going over what we're going to be looking at, because you can just plug in a function and graph it and see right away. You can also, online, you can use Desmos to get the same feature. Maybe Desmos is a little nicer, I guess. I'm going to give Kayla a couple more minutes here. She's coming back. So, for the rest of this class, we're going to take a closer look at the relationship between what we can figure out about a function, looking at derivatives, and what the graph looks like. Now, some of this is going to be really obvious, and some of it you have to kind of put your physicality of it into your brain a little. We'll see what I mean in a second. We're going to start with something really basic. If the derivative of a function is greater than 0 on some interval, the function is increasing. So, think about it, it's kind of obvious. If you have some function and the tangents have a positive slope, it has to be increasing. The function has to be increasing. Likewise, if the derivative is less than 0 on some interval, the function is decreasing. So again, if your tangent slopes are negative, you have a decreasing function. The book calls this the decreasing test. So let's do an example. We're going to take the function (3x to the 4th minus 4x cubed minus 12 squared plus 5), and we want to see where is this function increasing and where is it decreasing. So, okay, let's find the derivative. That's easy. The power rule, 12x cubed minus 12x squared. Was it that simple? Oh, 24x. Now let's factor that. I can take out a 12, right? And I can take out an x. I get x squared minus 12x. No. Minus x minus 2. Okay. Factor. So minus 2 plus 1. Right. So I can see this is going to hit 0 in 3 places. At 0, at 2, and at -1. So in between those, its sign is not going to change. So I want to break this up into 4 regions. 1, 2, 3. And in these different regions, see what the sign is, see whether it's increasing or decreasing. Okay. No, I don't really like the way I wrote this. Let me draw a better diagram. Well, I said 0 minus 1, 2, and so I have this is a region, this is a region, this is a region, and then this is here. Okay. Well, let's start over here. Let's pick a point out here, minus 2. So 12 times minus 2, minus 2 minus 2 is minus 4, minus 2 plus 1 is minus 1. I've got 3 negatives, so f prime is less than 0. So in this region here, it's decreasing. Right? Over here, we can try f of prime of minus 1/2. So 12 times minus 1/2 is minus 6. Minus 1/2 minus 2 is minus 2.5. And minus 1/2 plus 1 is just 1/2. 2 minuses, so this is greater than 0. It's increasing. All right, really plug in 1 pretty easily. 12 minus 1, 2, so it's negative again. So now it's decreasing, and I don't, yes?
Is it saying that the value that you're testing is, if the value that you're testing within like the derivative that you're trying to find is less than 0, then it's increasing on the interval, or is it saying that the derivative that you find is less than 0, then it's increasing on the interval?
I'm not precisely sure of your question, but I think I can answer it anyway.
Okay.
So we have this test that says where the derivative is greater than 0, it's increasing.
Yeah.
And where it's negative, it's decreasing. So I take my function, I find its derivative, and I guess I'm making an assumption here, which is like at these points right here, the roots 0 to -1, the derivative is 0. But between these points, it's going to stay, the sign is going to stay the same. So from here on out, I know the derivative is negative. So it's decreasing. You could restate your question if I didn't answer it.
No, I think you did. Yeah.
Okay.
Okay.
We can plug in 3, but I think it's pretty clear it's going to be increasing. So without knowing much else, we can kind of see that the function is going to come down, decrease. I'm sorry, I don't really know where it's going to. These points are where the derivative is 0. We know it's going to come down. It's going to go up. It's going to go down. And it's going to go up. That's not what it looks like. That's just kind of the rough outline. And we're learning this, again, by looking at the derivative. we gained that information from the derivative, but just to be clear, you know the dominant term here, x to the fourth, because you get far out either way, it's going to dominate. And since it's even, that's another way of telling that it's going to go up. Right? If this were odd, like this was, the function was 3, you'd know it's going to go down as you go to the left. You don't need calculus for that. Okay. So the next thing I want to put up here, we talked about maximum and minimums, and we talked about the fact that a local maximum or minimum takes place where f of x equals 0. But we didn't know necessarily from this whether that local extreme was a maximum or a minimum. So now we have what we call the first derivative test. First derivative test says when you're looking at these regions here, well, we know that the derivative goes to 0 at -1, right? But it's going from negative, derivative is going from negative to positive. So this extreme here, because we're going from negative to positive, we know it's a minimum. So if f prime goes from negative to positive, it's a minimum. Similarly, if f prime goes from positive to negative, it's going to be a maximum. So here we see, in this region, the derivative is positive, but then it becomes negative after the 0. So now we know that this is a maximum. And likewise here, we're going from negative to positive, so we again know it's a minimum. So by looking at how the derivative changes when it goes through 0, we can see what kind of local extreme we have, whether it's a maximum or a minimum. Now, we're not always this lucky. Sometimes, well, okay, how do we do this? Oh, well, what happens if f prime goes from negative to 0 to negative, or from positive to 0 to positive? Well, what would that look like? Well, an easy example would be f of x equals x cubed. Here we have a positive derivative, so we know it's increasing. It goes to 0, and then it's positive again. So in these two cases, you don't have an extreme. You don't have a local extreme. All right. So I have a different kind of example here we're going to take a quick look at. Here my function, we call it g of x, is x plus 2 times the sine of x. So we find the derivative. 1 plus 2 times the cosine of x. And we want to know where this is 0. Recall we give that the name critical point. Do you have a question? William? Did you have a question? No. So, cosine of x equals minus 1. Cosine of x equals negative 1/2. Oh, I guess I should have added here. We're interested in this function on the intervals between 0 and 2 pi. Okay, so how do we find the cosine negative 1/2? Oh. Go back to your unit circle. At some point where the adjacent over the hypotenuse is going to be 1/2, right? So does anyone recognize this angle? You have the hypotenuse 1 and the base 1/2. Do you recognize that angle? I think we talked about this before, but you have a equilateral triangle, and you drop an altitude. You know the angles are 60 degrees for equilateral. This divides the two angles, so it's 30 degrees. This is 1/2. And base will be square root of 2. So here we have that 30, 60, 90 triangle. 60-degree angle, or 60 degrees is pi over 3. So we have pi over 3 plus pi over 2. That's the way you get pi over 6. I think that's right. No, we don't. We have the wrong answer. Somebody help me out with my trigonometry. Cosine is negative 1/2, right? Should be, oh, this is 60, this is 30. That's the problem. So it's pi over 6. It's pi over 2. Which is 4/6. 4 pi over 3.
Professor,
Yes.
I don't think it's 4 pi over 3 because then it'll be over pi, the pi line.
All right, I'm going to go back to grammar school here.
It's
It's pi over 3, 3 pi over 4. It's
Oh,
pi over 6.
terrible.
So it is pi over 3, but because it's on that side, you have to do pi minus pi over 3.
It's pi over 2, right? It's pi.
No, it should be pi
Pi
minus
over 4.
pi
No,
minus pi over 3.
That's pi over 3, and then it's pi over 4, and then it's pi over 6.
Pi over 3 will be here.
Yeah.
That's a 60-degree angle, right? This is a 45.
Why do you have
5 or 6, that's a 30-degree angle. All right. So if I have a 30-degree angle here, that's pi over 6, right? From here to here. So I think it's pi over, shouldn't it be pi over 6?
It's
What's
2 pi.
over 2?
That angle is 2 pi over 3. That angle is 2 pi over 3. Not pi over 6.
This angle is 2 pi over 3.
Yes.
Yeah, that's, you're right. Okay. So x is 2 pi over 3. Okay. Are you happy with, I'm not happy with that, but everyone else is. But that's not the only place cosine is negative a half. It's also over here, right?
So that would pi plus.
And that's 4 pi,
Yeah, doesn't that work?
Yeah.
doesn't it?
4 pi.
Okay. My trig expert agrees. Okay, so we found the derivative is 0 at these locations. So we have from 0 to 2 pi over 3, 2 pi over 3, 4 pi over 3, and this interval 4 pi over 3, 2 pi.
Oh, so you're trying to.
So we want to know what the derivative is doing on in each of these regions. Okay, so here we could look at pi over 2. So the cosine of pi over 2 is 1 plus 2 plus 1 is positive. Between here, we can look at pi. Cosine of pi is negative 1. So negative 2 plus 1 is negative 1. Negative. And I guess we could look down here at 3 pi over 2. That's the cosine of 3 pi over 2. Zero. Right? You did that right. 0. So this is again positive. So we know the function is increasing here, and increasing here. And we know here it's a minimum, and here it's a maximum. I'm going to have to erase some of this. get this in. Now, we're not going through the whole process here, but this function is kind of going to look like this. So I did something wrong. Oh, positive to negative, I'm sorry. I have the test wrong. It's going to be a maximum and here it's going to be a minimum. So here's my maximum and here's my minimum. I shouldn't really put that arrow there. This is going to oscillate. Okay, so these are some tools we have for determining what a function looks like. We're not quite done, and the next part took me a long time to kind of get this kind of in my head. Before I go, though, are there any questions about this? I know I didn't really explain this perfectly clearly. So everybody okay with this idea? Look at the first derivative to see where the regions where it's positive and negative. Okay. This, I think, is the conceptually the hardest part. This section. It's really cool when you get it. Look at two curves here. What do we know about these two curves? Well, we'll just call this A and B. They're both increasing, aren't they? The derivative's going to be positive. But they're really different. Someone want to describe what's different about them? Think about that for a second. They're both increasing. They both have positive tangents. What's happening to the tangent here? Versus describe that?
For the first one, the slope is getting bigger, and then for the second one, the slope is getting smaller.
Yeah. Everybody take a look, right? In one case, the derivative, the function, the derivative is increasing. The other, the derivative is decreasing. All right, so we have a name for this. This is concave up. This is concave down. Another way of thinking about it is holds water. Right? Hold water in there. It's the opposite. Doesn't hold water. Okay. The pearl of wisdom here is that what's going on with the second derivative here? If the derivative is increasing, then the second derivative is going to be positive. The derivative is decreasing function. The second derivative is going to be negative. commute to San Francisco, you're entering a weekend where you get to understand what it's like to live in some country where we've invaded and we have airplanes, jets flying overhead, maybe bombs. It's kind of scary. We get the Blue Angels. Some people like it. But sometimes they fly very low to the ground and make lots of noise, and it's kind of scary. I think that's what we were seeing. I think we're starting to practice. Okay, so in relation to this, I want to draw a function that has both of these characteristics. On a region here, it's concave down, so the second derivative is less than 0. That's over here. And on the other side, we have the second derivative greater than 0. We have it concave up. Now what happens here? If this derivative, the second derivative, is negative and then it becomes positive, what happens? And it's smooth, what has to happen? It has to be 0. So we have here a point where the second derivative is equal to 0. And we have a special name for that called a point of inflection. This can have a lot of significance if you're looking at some real-world variable. You might have something like inflation that just goes up, right? It's very rare to have negative inflation. But sometimes it's increasing quickly and sometimes it's increasing slowly. And the point of inflection is where it's kind of changing that. Whereas it might have been going up. It's always going up. Whereas it's going up quickly now, hit this point where now it's slowing down. So you want to try, especially when you're doing the homework, get a feel for what this point of inflection is, what it looks like on a graph. It's sometimes hard to see. I hope I drew this and try to draw it back through. It doesn't have to, you don't have to have, the derivative doesn't have to be 0 here. You can have a point of inflection like this, where clearly the tangent is not 0. Okay, so given this idea, we have what's called the second derivative test. There's some, let me just write it, the second derivative. So you have to have a function which has a second derivative. That is, it has to be differentiable twice. Has to be continuous near C, some value C. Doesn't have to be continuous everywhere. And if the derivative of C is 0. And the second derivative, c is greater than 0, and f has a local minimum. That's kind of when we were looking at how the region was changing from positive to negative or negative to positive. The second derivative is telling us just that. If the derivative is 0, and the second derivative is less than 0, f has a local maximum. So by looking at the first derivative test, first and the second derivative test, you can tell, and you don't have the entire shape, but you can kind of see what the function is doing. All right. I'm going to try an example here. We're going to take f of x equal to x to the fourth minus 4x cubed. And we want to find out as much as we can about this, where its zeros are, where its minimums and maximums, and if it has a point of inflection, whether it's concave up or concave down. That's what we want to find here. So first we find the first derivative. It's 4x cubed minus 12x squared. And let's find the zeros. Okay. So it's going to be 4 by factor 4x squared times x minus 3. So the zeros has 2 zeros. Okay. And 3. That's the, I guess I didn't say that right. This is going to tell me where the zeros are, which is going to be what? X cubed times x minus 4. So it has a 0 at 4. But this is where the derivative is 0, which is where we're looking for local minimums and maximums. And let's see, the second derivative is now going to be 12x squared minus 24x. So if I look at where the derivative is 0, right, I'm trying to use my second derivative test, you can see the second derivative is 0. So that doesn't tell me right away what happens here. It tells me it's a point of inflection. So x equals 0 is a point of inflection. At 3, well, 12 times 9 minus 24 times 3. What's that going to be? 108 minus some number smaller than 108. It's going to be positive. So if the second derivative is positive, it's going to have a local minimum. So now we know at 3, it's going to have a local minimum.
It's like 0 and then number 2.
All right. See if we can get a feel for what this would look like for that actually correct. We know it crosses the axis, or touches the axis at 0. And then 2, 3, 4. What did I say? It's going to have a minimum at 3. So that means it's going to be going up afterwards. And it's going to have it's going to pass through 0. That's kind of what we're looking at. Or we can go this way. We don't have another. We don't have another. It's got a minimum here. Anybody watching me?
Professor?
Yes.
What about when x is 2? When x is 2, what happens then?
When x is 2.
Yeah.
Okay.
When you factor out the second derivative? Oh no, I mean second derivative. That
The
one.
second derivative is 2.
2 and 0
Yeah, what happens when x is 2?
is also
So 12x x minus 2. Well, the second derivative is 0, so that's a point of inflection. That's a point where the concavity is going to
Oh,
change. Yes?
but I think there's 2 inflection points. 0 and 2.
You're quite right.
yeah, that's what I was asking.
Okay. So I think you have something like this, where this is a point of inflection, and then, no, but it would be at 0, so, well, the concavity doesn't necessarily change. That's right. It's,
because the second derivative and x equals whatever x equals to makes sense will be a point of inflection.
this is fairly beyond my board capability. Let's do the old-fashioned thing. Put a few points here and try and use what we know. Okay, so it's as a point 0, 0, as a point 1 minus 4, so it's 1x minus 3. At 2, it's 16 minus 32.
No, I'm trying to graph the original.
It's still coming down. Oh, I get it. It's going to have a minimum down here, 3. Okay. And it's going to come back up to 4. I think that's what we've got here. Okay, so the question now is where are the So what happens at 2? I don't think I have the artistic talent to draw it, but I think what happens here is you have a point of inflection. So, I don't know, something like this happens here. I guess this wasn't the best example. All right, well, my apologies. I'll find a better example for Tuesday so that I can illustrate this a little better. There's a homework assignment. I think it's for Thursday, but if it says for Tuesday, just make believe it's for Thursday. gonna write me an email and I'll change it. Don't worry about it that much. Okay, I'm kind of tapped out here, because I kind of messed up, but we can go now. Or come in asking questions.